let's delve into the world of electrochemistry. So at this point in the semester, you're probably tired. A lot of you guys are finishing up. It's one of the last topics you're going to cover. But honestly, electrochem is really fun, in my opinion at least. It's electricity applied to chemistry. We're either using electricity to cause a chemical reaction to occur, or we're using a chemical reaction to harness some electricity. So let's get into the differences. Module 20A, I'm going to go ahead and do a little bit of a review. So we're going to do a brief introduction to electrochem as a whole, and then we're going to review some stuff you should have learned in Chem 1 with redox titrations and reduction oxidation numbers and all that kind of stuff. So electrochemistry itself is the study of the interchange of chemical and electrical energy. Again, I am either using a chemical reaction to harness electrical energy or using electrical energy to cause a chemical reaction. We could have a spontaneous chemical change that can be used to produce electricity, like your batteries, or we can use electricity to produce a chemical change, like electrolysis. So hopefully this part is a review, but if it's not, it's okay. We'll go through it slowly. Oxidation and reduction. We have to remember that oxidation means that we are losing electrons, and reduction is gaining electrons. Two different mnemonics we often use or often find to remember this is Leo the lion goes grr or oil rig. Leo the lion goes grr stands for losing electrons is oxidation, hence I apologize, let me put it back onto a pen, L-E-O for Leo, losing electrons is oxidation, and goes grr, gaining electrons is reduction. The other common mnemonic we'll see is oil rig, where it stands for oxidation is loss, reduction is gain. Of course, we have to remember then the word of electrons. So oxidation is loss of electrons, reduction is gain of electrons. If the species loses its electrons, it has been oxidized. If a species gains electrons, it has been reduced. An oxidizing agent is like, in my mind, a real estate agent. It's not doing what the name says, it's causing that to happen to something else. What do I mean? I mean, an oxidizing agent is a substance that oxidizes another species. It itself is reduced. So it's not being oxidized itself, it's instead oxidizing something else. It's accepting someone else's electrons and allowing itself to be reduced. It's like a real estate agent, right? Real estate agent isn't selling homes to themselves, they're selling them to you. A reducing agent is a substance that reduces another species. The substance itself is oxidized. So again, the other way you kind of do it is students think about it opposite. So they think oxidizing agent, that means it has to be reduced, so therefore we find the species that's oxidized. Whichever you remember it is fine. Just remember, if it's an oxidizing agent, as acting as an agent, it is not itself oxidized. It is reduced. It's oxidizing something else. Oxidation states and numbers. These throw students off a lot. An oxidation state or a number is a way for us to just describe the flow of electrons. So the easiest way to approach oxidation reduction reactions is by first focusing on your oxidation state of each element. From there, you can determine what's changed. And once you know what's changed, it's much easier to do these reactions. There are 4 rules that we follow when assigning oxidation states or oxidation numbers. And I do want you to remember that these numbers are a made-up convention, okay? But they often correlate to the charge on a species. Rule number 1, the oxidation number of an element in its neutral elemental form is 0. So, what is the oxidation state of each element in the following substances? If I have Cl2 gas, chlorine is a diatomic. Its most stable form is as Cl2. Therefore, the oxidation state here will just be 0. O2 gas, same thing. Oxygen gas is one of our 7 diatomics. It is most stable as O2 in the gas phase, so it will be 0. Fe solid, that's just iron metal. Iron metal, in its most stable state, will have an oxidation state of 0. Carbon graphite. Graphite is actually the most common form, or the most stable form of carbon, and so now that it's in its most neutral stable form, it's going to have an oxidation state of 0. The oxidation rule number 2, the oxidation number of a monatomic ion, monatomic just means single atom, ion, is the same as its ionic charge. Again, this is coincidental, okay? It matches the charge of the ion. So if I look, I'm going to zoom in here. If I look at Al2O3, it's kind of like splitting this back up to think about naming, okay? We know that aluminum always has a +3 charge. The oxygen here will have a -2 charge. How do I know that? Well, first, oxygen likes to be -2 or 0. It almost always is. I say almost. We'll see an example where it's not in a few minutes. But aluminum, we know, is always a +3 charge. Overall, the oxidation states have to equal out to the charge of the element, the species itself. So we see here aluminum oxide is a neutral compound. I have 2 Al3 pluses and 3 O2 minuses. Overall +6, -6, and a 0 charge. So Al2O3, the aluminum, is +3. The oxygen is -2. That means each individual aluminum, the aluminum itself, is +3. The oxygen itself is -2. Okay? It doesn't mean overall. It doesn't mean Al2 is +3. It means each individual species has that charge. So again, although I just erased it, I have 2 aluminums, +3 each, overall +6. I have 3 oxygens at -2 each, overall -6. If I look at FeO, now Fe we know can have a variable charge state. We can have iron +2 or iron +3, so we use our oxygen to determine the charge on that species. In this case, I know oxygen is going to be a -2 charge, so this iron must be a +2 charge. The oxidation state on this oxygen is -2. The oxidation state on this iron is a +2. If I look at Fe2O3, oxygen, again, really likes to be -2 if it can. I have 3 oxygens with a -2 charge, so overall -6. I have 2 irons. They must overall equal a +6 charge, so I have a 0 charge here. Therefore, each iron must be a +3 charge. So again, it's 1 iron is +3, 1 oxygen is -2. And if I look at Na2S, sodium is a group 1 metal. It's an alkali metal. Group 1 metals always have a +1 charge. So I have 2 sodiums. They each have a +1 charge. Overall +2. I have 1 sulfur. It must equal a -2 charge to give me an overall 0 charge. So it must be a -2 charge. Again, that means each sodium itself, the sodium has a +1 charge. The sulfur has a -2. I just happen to have 2 sodiums to counterbalance the charge on that sulfur. In binary compounds, the element with the greater electronegativity is assigned a negative oxidation number equal to its charge in simple ionic compounds of the element. What do I mean by that? We're going to work some examples here at the bottom. But if I have binary means 2 compounds, means two elements in it. So the one with the greater electronegativity is going to be the negative oxidation state. The one with the more electropositive element is going to have the positive oxidation state assigned to it. The sum of the oxidation state also equals the overall charge of the species. So let's go ahead and work some examples here. If I look at H2O, again, these are binary. It is a neutral compound, so overall it has to add up to a 0 for the species. And I've got hydrogen and oxygen. Oxygen is the more electronegative species here, so it's going to carry the negative charge. We know oxygen prefers to be a -2, so we are going to go ahead and give it a -2 charge. The species overall has to be neutral, so each hydrogen must be +1. I have 2 hydrogens, +1 each, giving me +2. 1 oxygen at -2, giving me an overall -2 charge, and overall it is 0. So here, hydrogen +1, oxygen -2. How does this factor into something like hydrogen peroxide, H2O2? What we would do conventionally, we would expect is to give that oxygen a -2 charge. We would want to say, okay, -2 on the oxygen. There's 2 overall oxygens, so a -4 charge. and we would say 2 hydrogens have to be a +4 charge. And we would want to say that means the hydrogen would be a +2. The thing is, we can't do that. That is a giant no. Why is that a giant no? Because what that is emphasizing is it is trying to state that hydrogen has lost 2 electrons. One hydrogen atom does not have 2 electrons to lose. One hydrogen atom only has 1 electron it can lose. So hydrogen can either be a 0 or a +1 charge, but it can't be greater than +1 because it doesn't have any more electrons. So what we actually find here is peroxide is one of the exceptions. Peroxide will have a +1 charge for the hydrogen. So I've got 2 hydrogens at +1, giving me an overall +2 state. That means my 2 oxygens have to give me a -2 to be a 0 charge. So each of my oxygens must be a -1 charge. A little bit different than what we've learned and doesn't follow the trend, but again, it's because hydrogen just cannot give me more than 1 electron. It doesn't have them. Each hydrogen, though, will be +1. Each oxygen in peroxide will be a -1 charge. What about PCl3? I'm going to go, this is a molecular compound, so I know that phosphorus prefers to be a -3 charge, but I've got to add something up that equals overall to a 0 state here. And I know that the more electronegative element is going to have the more negative oxidation state. So I'm going to give that negative oxidation state to the chlorine. So I know chlorine is a halogen, and halogens like to have a -1 charge. I have 3 chlorines with a -1 charge. That's giving me an overall -3. My 1 phosphorus has to be equal out to a +3 to give me a 0 overall charge here. Again, that means each chlorine is -1 and my phosphorus is +3. I just happen to have 3 of the chlorine to equal out to that overall -3 charge. What about PCl5? I just established that chlorine wants to be a -1 charge. So I have -5 from the chlorine. My 1 phosphorus has to be equal to +5 to give me a 0 charge here. So now I see my chlorine is still -1, but now my phosphorus has jumped up to a +5 state. Again, these are oxidation states. Phosphorus has up to 5 valence electrons it could lose if we're talking about the transfer of electrons. So my phosphorus, +5, my chlorine, -1. What about nitrate versus nitrite? I'm going to go for the more electronegative element first. So I'm going to look at my oxygen first. And I have 3 oxygens here. Each oxygen wants to be a -2 charge. So overall, -6. This has to equal an overall -1 charge because the species itself is an ion and has a -1 charge to it. So that means that whatever I'm adding it to must be +5. My 1 nitrogen must have a +5 charge to give me an overall -1 charge. So I find my oxygen to be -2, my nitrogen to be +5. What about NO2? NO2 minus, nitrite. If I look here, I've got oxygen as my more electronegative species again. This time I have 2 of them. 2 oxygens times the -2 charge gives me an overall -4. This has to overall equal a -1 charge, though, because, again, I have a -1 ion here. I have an anion with a -1 charge. I have 1 nitrogen. I have to add 3 to get to that -1 charge, so that nitrogen must be a +3 charge. -2 on the oxygen, +3 on my nitrogen. So some generalizations. Number 1, metals can only have a positive oxidation state or be equal to 0 if they're in their standard state. Metals are not gaining electrons. Don't give the metals electrons. They don't want them. Remember what we talked about in Chem 1, metals only want to lose electrons. They don't want to, they can gain them if they're going from a positive state to a neutral state. That's what we call being reduced, but they can't go beyond negative. They can't go beyond 0. They don't want to go to a negative charge state. So the metals either want to be at 0 or they want to lose electrons. If they're gaining them, it's because they're going back to a charge state of 0. They're being reduced down to 0, such as taking magnesium ion, giving it 2 electrons, and making magnesium metal. That is fine, but I'm not going to take a magnesium metal and give it electrons from there. Nonmetals can have both positive and negative oxidation states, or be 0. So nonmetals can do whatever you want. They can go positive, negative, or neutral, or completely 0, but metals only positive and 0. The highest oxidation state that an element can have is the old group number. We call these the Roman numeral numbers. On the new periodic table, and I don't have one up in front of me right now, and I apologize for that, but on the old periodic table, we have your S block, we have your D block, we have your P block. And that's your halogens there. They used to have numbers where now they're numbered 1, 2, 3 to 12, 13, 14, 15, 16, 17, 18. But they used to be numbered 1, 2, 3, 4, 5, 6, 7, 8. If we ignore your transition metals and just count across the table 1, 2, and then group 13 becomes group 3, 14 is 4, 15 is 5, 16 is 6, 17 is 7, 18 is 8. That tells you the highest oxidation state that element can have. So like a noble gas can have an oxidation state up to a positive value of 8. The halogens can have an oxidation state up to a positive value of 7. The lowest oxidation state that element can have is the old group number minus 8. So for example, oxygen is group 6 in the old naming convention, which means oxygen can go from plus 6 to negative 2. Phosphorus is group 5. It can go from plus 5 to negative 3. So, you might want to pull out your periodic table for this, because it might help. But what is the highest oxidation state that chlorine can have? When I look at chlorine, I know chlorine is a halogen. Its current group is called group 17. But that means that its old group number was group 7, which means the highest oxidation state it can have is a plus 7 charge. What's the lowest oxidation state that chlorine can have? Well, it's that old group number minus the number 8, or a negative 1. Which shouldn't surprise me, right? Chlorine wants to gain 1 electron to be like a noble gas. So the fact that chlorine can gain 1 electron and have a negative 1 oxidation state is not surprising to me. What's the highest oxidation state that magnesium can have? Magnesium is an alkaline earth metal. In group 2, which means the highest oxidation state it can have is a plus 2. What's the lowest oxidation state magnesium can have? Some people are going to tell me 2 minus 8, negative 6, but I need to recognize that magnesium is a metal, which means the lowest oxidation state it can have is 0. Let's go ahead and work some more examples. Determine the oxidation state of each element in the substances below. I'm going to zoom in. If I look at CO2, oxygen is more electronegative than carbon, so oxygen is going to carry the negative charge. Oxygen is going to be a negative 2. I have 2 oxygens, negative 2, overall negative 4. Has to equal 0 because carbon monoxide is a neutral species. 1 carbon must be a plus 4 charge to equal out to a 0 overall state on the molecule itself. What about NaCl? I look at NaCl. I know chlorine is the more electronegative of the 2 species. Plus, it's ionic compounds. It's pretty easy to split apart, right? I've got 1 chlorine. It wants to be negative 1. My 1 sodium must be plus 1 to balance that out. Plus, sodium is an alkali metal. It likes to be positive 1. What about this phosphorus here? P3 minus. This is actually kind of easy. It's telling me right there what the charge is. The oxidation state on this phosphorus, -3. Just like it reads. What about P4? It's kind of confusing because there's nothing else here except phosphorus, right? Does that mean that one phosphorus has an oxidation state of, say, +5 and one is -3 and they all balance out somehow? No. Phosphorus is one of your polyatomics. It's quite happy being P4, and so the oxidation state here is just 0. If you see an element listed by itself like this, it's probably, and it doesn't have a charge to it, whereas the phosphorus here had a charge to it. This one does not. It's probably 0. FeCl2 and FeCl3. I know chlorine wants to be a -1 charge. I have 2 of them here, overall -2. This has to add to 0, so it must be a +2 charge for my 1 iron. When I look at FeCl3, I have 3 chlorines here. Overall -3 for the chlorines. I need a 0 overall charge for the compound, so that 1 iron must have a +3 charge. Let's move over here. Okay, what if I add more than just 2 elements? What if I'm not using a binary compound anymore? I've got sodium nitrate. In my mind, you can do whatever you want. In my brain, it's easiest to separate out the polyatomic from the rest of the species first. That's how my brain sees it best. So what I do is I write Na plus and NO3 minus. I then start looking at oxidation states. Na plus, tell me right there, +1 for the sodium. I'm going to write it up here just so we don't get confused. Now I've got nitrate. I've already done nitrate previously, but let's work through it again. I've got 3 oxygens here and 1 nitrogen. Oxygen is my second most electronegative element on that table, right? Nitrogen is tied for third against chlorine. That means oxygen is more electronegative, so it's going to hold the negative charge. Oxygen wants to be a -2 charge. I have 3 of them, so it's overall -6. This has to equal a -1 charge because I have nitrate. It's got a -1 charge to it. So I must add 5 to this to allow that -1 charge for the compound, which means the nitrate or the nitrogen portion of this is +5 and each oxygen contributes -2. What about SCl2? I've got sulfur and 2 chlorine. So chlorine is more electronegative than sulfur. Chlorine wants to be -1, overall -2. I need a 0 charge, which just means that sulfur must be +2. +2 -1. H2S. I've got 2 hydrogens, 1 sulfur. One thing you can just remember is you can either do by electronegativity or remembering that hydrogen can't lose more than 1 electron. But let's do by electronegativity first. If I look at it that way, sulfur is the more electronegative, so it's going to be a -2 charge, overall -2. But I need to equal to a 0 charge. I have 2 hydrogens that need to equal to a +2 charge, so they'll each be +1. The other way to think about this is hydrogen either has to be 0 or +1 because it doesn't have any more than 1 electron to lose. And if I have 2 of them, they were +1 each because it's not just hydrogen in the compound, it's going to have an oxidation state. Then I know the sulfur would have had to be -2 as well. What about SO4 2 minus, sulfate? I've got 1 sulfur, 4 oxygen. Oxygen is the more electronegative species here. And I know the oxygen wants to be a -2 charge, which is overall -8. And the species itself has an overall -2 charge. That means I must have +6 for the sulfur. 6 minus 8 gives me my -2. I know my sulfur is +6, and each oxygen is -2. What about S8? Again, that might be look a little confusing to students, but sulfur is one of those that's a polyatomic. It's one of the ones we memorized in Chem 1 along with our diatomics, right? Sulfur likes to be S8. It's its most stable form. So this will actually have an oxidation state of 0. Again, I only have one element listed, and that element is not charged. That 8 is not superscripted as a subscript, meaning there's 8 of them together. So therefore, it's pretty safe bet, even if I don't remember that it is the most stable form, that the oxidation state is going to be 0 here. What about Na2SO3? This is one of those cases where, again, I would split it apart between the element and the polyatomic. So I've got 2 Na pluses and an SO3 2 minus. The Na plus is telling me right there, +1 charge. Now I've got sulfite instead of sulfate. So I've got 1 sulfur, 3 oxygen. Oxygen is a more electronegative species. 3 times -2 is an overall -6. I need an overall -2 charge. So this must be +4. If sulfur was 4 minus the 6 from the oxygens, I would have an overall -2 charge. +4 and -2. Let's bring that back down to size of screen. Okay. Now, based on the last 5 sulfur-containing compounds on the list, what are the possible oxidation states of sulfur? Well, let's see what we got here. We've got a sulfur of a +4. We've got a sulfur of a 0. We've got a sulfur of a +6, a sulfur of a -2, and a sulfur of a +2. So let's go ahead and put those in order. -2, 0, +2, +4, +6. What do I notice? I notice that for sulfur, I am going from, sulfur is your group 6, or it's group 16 now, which means old group number 6. Highest oxidation state I saw was 6. The lowest oxidation state it can have is the old group number -8, -2. And then I realize I'm literally going every 2, 2, 4, 6, -2 to 0 to +2 to 4 to 6. It's jumping in increments of 2. You're going to see trends like that in your oxidation states. There's going to be species like phosphorus that we saw in the previous, or 3 slides ago, I apologize, that liked, sorry, wrong button, that liked +3, +5. And I see phosphorus down here with a 0, -3. Everything will pass through with 0. Everything can have a 0 oxidation state. But you're going to see trends within the other elements that are going to happen as well.